Hello, everyone. Yes, welcome to the collaboration session. I'm Bo Yu Gao from the Jinan University. So in this session, we will have 4 presentations. Each has 12 minutes presentation, followed by 3 minutes questions. The first one is about the first presentation presented by the Hyun Cho from the University of the South Australia. The title is about the title is biochemical collaboration using spatial temporal cues to collaborate across time and space on physical tasks. So please.
Hello, everyone. I am Hyun Jo. Today, I am excited to present our work by cross collaboration using spatial temporal cues to collaborate across time and space on physical tasks. Our research is driven by key challenges in remote collaboration for physical tasks. So we often categorize collaboration using the time-space matrix. This framework helps us to understand how we work together based on time, synchronous versus asynchronous, and space, co-located and remote. A lot of collaboration research has explored different quadrants of this matrix. For synchronous remote collaboration, the challenge is sharing spatial context effectively. Researchers have explored avatars, 360-degree cameras for streaming, and shared virtual replicas to bridge the physical distance. More recently, there has been growing interest in asynchronous remote collaboration to support work across different time zones. In XR, this means we can go beyond simple text messages and share rich spatial temporal cues, such as replaying users' past actions or leaving 3D annotations in the environment for someone to review later. However, real-world collaboration is rarely confined to single quadrants. Workflows are often blend of both modes. For example, an expert might need to review novices' past actions during a live session or rewind time to correct a mistake that just happened. This fluid transition between synchronous and asynchronous states is what we call bicross collaboration. Our research focuses on designing the spatial temporal cues needed to support this flexible model. This leads us our central research question: how do different spatial temporal cues influence collaboration effectiveness in physical tasks? The scenario is as follows. A novice worker performs a task, physical task, and their actions are recorded. If there is an error, a remote expert reviews this recording asynchronously to find the problem. Then, novice and expert join in a live synchronous session to fix the error together, using the recording as a shared reference. To enable this, our system connects a local novice in AR with a remote expert in VR. It is designed to seamlessly support the entire workflow from the initial assembly and recording to the asynchronous task review, and finally, to the synchronous collaboration for error correction. So here you can see how the novice's AR view and the expert VR view are connected, allowing both asynchronous and synchronous interactions within the shared virtual space in the middle. So we designed and evaluate the 3 spatial temporal cue interfaces for novice workers recording and how to visualize it. So first, the 2D, which serves as our baseline condition. It is the first-person view video with a standard timeline just like as the simple video playback. And secondly, the 3D basic condition, so which visualize the recorded action with an animated avatar and virtual object replicas to shared 3D space. And finally, the 3D action, which enhances 3D basic by adding automated event-based bookmarks for key moments like grabbing or dropping an object. So to elaborate more on 3D action queue is our key innovation here. So instead of simple linear timeline, so it automatically creates bookmarks for important events, like when an object is grabbed or released. This allows the expert to instantly jump to most critical moments of the task instead of searching or through the entire recordings. So the yellow color is the automatically generated events on a timeline. So based on this design, so we formulated 3 hypotheses. So H1 is about the asynchronous review. The 3D queues will lead to better task performance than 2D queues. It's about the more about the objective measurement, and H2 is for synchronous collaboration. 3D queues will again yield better performance than 2D. And lastly, H3 is compare 3D and 2D, so more about the subjective measurements. And we designed and conducted user study with 28 participants to test these hypotheses. The study followed a 3-step procedure mirroring our bichronous collaboration scenario. So bottom right side is a manual given to both novice participant and expert participant. Then novice participant instruction have some initial errors, and expert instruction have a perfect correct instruction is given to expert. So novice worker have to assemble some specific shapes. It visualized in upper right-hand side images. So novice worker have to assemble that specific shape using the SOMAQ blocks, and for step 1. And the step 2, the expert worker asynchronously review the recording to find errors. So lastly, step 3, both users collaborated synchronously to undo and correct the mistakes. And each participant experienced all 3 interfaces, 2D, 3D basic, and 3D action. So we collected both objective performance data and subjective feedback through the standard questionnaires. And this is a short video, the video demonstration about the user study. So this is step 1 for novice workers' initial task. Novice worker have to assemble to grab the object and assemble the specific shape in a work table in the middle. So when step 1 is end, the expert worker can have novice workers recording spatial temporal cue, then novice expert worker review the video and find the error. But in 3D action condition in the right-hand side, novice expert worker can quickly jumping between the bookmarks. And lastly, this is a step 3. So in step 3, then seamlessly guiding to novice between expert and novice worker to correct the task in real time. So our results clearly support our hypothesis. For task completion time, participants were significantly faster using the 3D action interface in both asynchronous step 2 and synchronous step 3 phases. So we saw a similar pattern for head rotation and timeline manipulation as well. The 3D action interface required the least physical movement and the least interaction with the timeline slider, demonstrating its efficiency. And for the subjective measurement, this data also shows a similar result. The 3D action interface was associated with significantly reduced the task load and increased the system usability and higher spatial presence scores compared to the other conditions. So when we asked the participants to rank the interfaces, so 3D action was the overwhelming favorite for both novice worker and expert workers. In summary, our discussion highlights two key takeaways. First, regarding 2D versus 3D, our results confirm that 3D interfaces are superior for physical tasks as they provide essential spatial context that speeds up error detection and clarifies guidance. The 3D action interface was particularly effective because its bookmarks minimized the manual searching. The second, regarding the subjective experience, 3D interfaces were strongly preferred and led to lower cognitive load and higher usability, that confirming our hypothesis 3. Yes, we have our work has limitations as well. So firstly, users sometimes frequently actually lost track of the object in their field of view. So our future work could be explore more visual effects like trajectories or world in miniature visualization to mitigate this. Second, our findings are based on the large-scale assembly task with using toy box like Soma cube blocks, and it may not generalize to real-world tasks requiring fine motor skills like some tabletop, assemble some complex machines. And finally, our bookmarks are currently rule-based. An exciting future direction is to use AI-driven behavior recognition to create more intelligence and context-aware bookmarks. To conclude, we introduced and evaluated Biochronos XR collaboration system. Our main contributions are we propose the concept and implement of this blended asynchronous and synchronous framework. And we also designed the spatial temporal cues, 3D action bookmarks on automated event-based mechanism for efficient navigation of recorded content. And lastly, so we had controlled user study whose results demonstrate on embedding task semantics to directly into the timeline interface and dramatically improve the efficiency of both asynchronous review and synchronous problem solving. Thank you for the attention. Yeah.
Yes.
So I'll be happy to answer any questions you have.
Yeah, thank you for the presentation. Is there any questions from audience? Okay.
So you mean so we have, okay.
Okay, thank you for your presentation. I have a question about your study design. I want to know like what kind of information you are recorded from the user's action. For example, if you also record the 6-fold 3D position and the rotation information of user's body.
So we recorded, thank you for the question. We recorded users' behavior and to generate the spatial temporal cue. So I mean the playback video in 3D video. So actually we have additional slide here. Oh yeah. So we recorded users' head movement and users' hand posture, and also object 3D 6DOF tracking data as well. It contains timestamp and 3D position and rotation information. So that using that information to make some 3D spatial temporal cue, including the avatar's movement, avatar's animation, and virtual replica of task object. Yeah. Thank you.
Okay, thank you. Is there any other questions? Okay, thank you.
Thanks for your presentation. You mentioned the 3D interfaces were preferred by the users. Your task was pretty 3D based. So do you think if you had something like an electricity board installation, which is much more 2D task, would that give different kind of results on the referral of the users?
Sorry, but could you explain one more time? Yeah.
I mean, the task that you had putting those cubes together, that's pretty 3D based task.
Yes.
But if you had something that's more 2D based task, like doing installation on an electric board, would the users prefer the 2D interface in that case?
Yeah, that's right. It's our task design is more like a 3D object movement in some large space. I think so. That's why there is the future direction would be including more a variety of task design, like tabletop object manipulation using the 3D, 2D information as well. So yeah, I think that could be some more, maybe some future possibility to some for our future studies. Thank you.
Okay, so due to time limitation, so if you have more question, please may discuss with the speaker interactive, yes, after the presentation. So let's move to the second presentation. Let's thank the speaker again.
All right. Well, thank you for the introduction. Today, I want to present how see-through tutorials and group transitions can improve onboarding of multiple users into a VR application. And at this point, I would also like to thank my colleagues, Tony and Anton, my former student Pramod, and my supervisor Bernd Fröhlich for their support. So in our group in Weimar, we are researching museum experiences for multiple users. And in this context, we're often giving demonstrations to different variety of audiences, and they often have different technological backgrounds. And a core challenge that we are often facing is to have all users ready for the VR experience at the same time. And we believe that such a synchronous start in an app is important and that it has benefits for the overall user experience and also for the group cohesion. And of course, reasons that users arrive delayed in the VR app is either because they had to maybe like put on the headset in a different way, or they had struggle comprehending some of the instructions, or they are in VR and forget certain inputs and then have to ask the guide. Or of course, there might be also some assistance needed outside of VR that requires the guide to take off the headset again. And in my talk, I now want to show how pass-through and group transitions can improve this onboarding procedure. Before we get into the approach that we are using, I want to quickly mention the approach that we've been using so far. And this is typically involving a form of onboarding stage. And this is also done by a lot of other practitioners. I guess most of you know this too, where you basically start in the physical world. You give the users instructions on how to put on the headset and how to use the controls. And of course, there has been a lot of related work in this on how to improve these explanations. And for example, some people use video tutorials. And Chauvin et al. Have also observed that there's kind of a trend that some of the users have this form of wow effect where they just rush through the instructions because they want to get into VR because they're excited. And then they don't know how to control the application. This is also something that we have observed with school classes, for example. And once all the instructions are given to all the users, we can then typically put on the headset and immerse ourselves into the virtual reality application. And of course, there we are then isolated from the surroundings. And what is recommended by Chauvin et al. Is that users get assistance in this phase. And this could either be tooltips, or this could be additional video that for the guide that can then observe what the users are doing and help them if needed. In our applications, most of the time, the guide can join the users within the VR application and then kind of guides them through the museum. So they can also help from within the application. Afterwards, typically we take off the headsets and then emerge back to the real physical world. This is kind of the approach that we've been using so far, and I think that it's integral to have these onboarding sessions for good user experiences. However, what these typical onboarding sessions do not solve is the problem that people still arrive at different times, and if there's problems, they still have to go out of VR. And this is mainly due to the fact that all the onboarding literature that I have found is mainly focused on single users and never really on multiple users. And this is what we are trying to tackle with our approach. So with our approach, we want to make use of these new see-through and pass-through capabilities that are typically there now with the latest VR headset generations. And this allows us to directly start with putting on the headset, mitigating the wow effect, so users can directly get into VR. However, we don't show VR, we first go into kind of a see-through stage where users can see each other still, so they are not isolated, and they can, for example, see name tags. And we use this stage then to give instructions, to have interactive tutorials. And here it's useful because you can observe other users, what they are doing. You can observe the guide, how some interactions are done. And after that, of course, then you still need to enter VR. And what we are then here suggesting is to use transitions. There has been a lot of work on transitions. For example, there are different transition styles, different transition metaphors. And there's a lot to pick from, basically. However, all of the known transition papers that I've read only focus on single user transitions, and there's like kind of this gap for how do we transition multiple users. Once all the VR users are in VR, we can then still further assist them. And of course, if there's a need, they could either go back to the see-through stage or emerge and take off the headset. And this summarizes our general see-through onboarding procedure. And we think that it mitigates the wow effect, isolation, and disorientation, and that it's good because it supports that users can learn through observation and directly test interactions when you learn them. So in order to test this framework, we implemented it in Unity with the following toolkits and devices. And one question, of course, remained, and that is how to now transition groups instead of single users into VR. And for this, we thought it makes sense to categorize like how many users are moving at a time. So we found that, of course, every user could transition individually. Users could transition after each other, like walking through a door, like the typical portal metaphor, or they could transition collectively. And we then implemented specific instances of each of these transition types. So we first came up with a magic box for the individual transition. Here you can see that the user gets a magic box, and when they open the magic box, they are then transitioned into VR. And what is important in this individual transition is that the users are still in the room, so we need to display some kind of ghost avatars in order to avoid that users bump into users that they are not seeing anymore. In the sequential transition, we basically implemented a form of portal, so we had a magic door that could be placed by the guide, and then users could walk through this door and transition into the museum room. And of course, this is also nice that you have a kind of a preview of where you will go to. And then here we can see how other users transition into this room. And finally, for the collective transition, we were inspired by the Harry Potter port keys. So we thought that we implement a magic table where users can put their hands on together and then use this to collectively transition into the museum room. We had two research questions on the framework and on the transitions. The first one was, does our onboarding framework improve the introduction of co-located groups into VR? And the second was, which group transition strategy is best suited for onboarding and what are their respective advantages? To answer these questions, we conducted a user study with 12 triads, so always 3 users, ending up with 36 participants. And we used a within subject design with Latin square counterbalancing. And our independent variable was the transition technique. The first one was the put on transition, which basically just means putting on the headset. And the other ones were our just shown pass-through transitions. The procedure was as following. We welcomed our users and gained their consent. We then showed interactive tutorials, a painting and a scaling tutorial that were then later swapped later on throughout the study. And here you can see how users can learn and prepare how to then later on fulfill a task in VR. And for the scaling tutorial, similar, users learned how to scale with our implemented interaction for scaling. And they could observe this done by the guide. And of course, here you can see that they could use it as well. After that, we then transitioned into VR using one of the transition techniques. And in VR, in our museum room, users had then to fulfill a task, either a painting or a scaling task. So in the painting task, you can see here the white objects in the background had to be colored. And in the scaling task, users had to bring objects to their original position and scale them in the right size. For example, here the bench or the figure in the background. After this, we had users fill out a questionnaire with the following measures. I will not go into detail here due to time. And this was then repeated 4 times for each transition type. And we finalized with a closing questionnaire. We set up the following hypothesis before the study, and I will not go into all of them. The first one was the overall rating would be the lowest for the put-on transition, that the connectedness would be the highest for the collective transition, and that continuity would be the highest for the sequential transition. So let's have a look at our results. For the rating, we found that all our pass-through transitions received a significantly higher rating than the put-on transition. Therefore, we accepted this hypothesis. For the connectedness, we found that collective and sequential transitions yielded higher connectedness scores. However, not always significant, so therefore we only found partial support for this hypothesis. And for the continuity, we found that the put-on transition yielded significantly lower continuity scores than all the other pass-through transitions. However, the sequential transition that we thought would be scoring the highest did not do so, only in confront of the put-on, so only partial support or reject. In terms of feedback that we collected from the users, I will just mention a few of them. Put-on was considered easy to use. However, the transition was too abrupt. Collective onboarding or transition was considered collaborative and immersive. Sequential was considered realistic and easy to use and intuitive because it was basically a door that you had to walk through. And individual was fun and engaging, and the users liked the visual effects. So in summary, all our group transitions outperformed the traditional put-on approach in overall rating, continuity, and connectedness. And we therefore strongly recommend to start onboarding sessions in a see-through mode rather than instructions and then later putting on the headset. And also we showed that our transitions have all different trade-offs. We found that the collective transition increases group cohesion, individual transition provides users with more agency, and sequential transition was easy to use and appeared more realistic. So I recommend to either combine these transitions or choose them according to the scenario where we want to onboard the users to. And this concludes my talk, basically. We introduced a comprehensive multi-user onboarding framework for multiple co-located VR users. we defined and analyzed 3 group transition strategies, and we conducted a user study to show that this improves onboarding and that the transitions have different trade-offs. And in our paper, we then give a few recommendations on how to onboard multiple users. And with this, I would like to conclude my talk and thank you for your attention. I'm also happy to answer questions.
Yeah, thank you for the presentations. Is there any questions from audience? Okay, I have a small question. Like from your slides, I see the 2 simple tasks, painting and also the scanning task. So have you considered extending your task to more complex, like assembling task or yeah?
Yeah, so that's overall like a little, I wanted to measure time, but then groups were like so separated on how quickly they could solve tasks. And since it's collaborative, some users would, if somebody's really good, he would just jump in and do the more complex task for the users that don't understand yet. So I'm also mentioning this as the limitations of our paper. Like there's definitely need for improving overall this testing of this assumption. However, in the sessions where we had just instructions without any see-through and then transitions to put on, already there we had in each of these triad sessions that started with the instructions, we always had at least one participant that had like struggles with the controls. So definitely something more difficult would be better to kind of like test the limits here, of course. Yeah.
Okay, thank you. Okay, so if we have no other questions, so we may thank the speakers again. And then,
Okay, so thank you. Yes, I'm going to present to you my paper on virtual workspace configurations for collaborative hands-on learning. So to begin with, when we think about real-time collaboration, usually we are going to think about something like that or something like that. So this is real-time shared collaboration, so real-time shared workspace with avatars that can be more or less realistic. But while this can be very good in some contexts, it might not be appropriate for all contexts, such as the educative context. Indeed, in the educative context, collaboration is something that is very interesting for learners. For instance, some studies find advantages such as the fact that students can build on each other's knowledge, also improve their critical thinkings. And so when it's done, usually it's in real-time shared workspace. But recent work on desktop by Cheng and colleagues showed that individual desktop also have advantages, such as improving the learning outcomes. But we don't know if it will also work best like that in a collaborative virtual environments. So with these informations, we decided to investigate these different types of workspaces in collaborative hands-on learning. So we implemented 3 different workspaces for that. First, a shared one. So this is basically the same as the real-time shared workspace that I was talking about earlier. So here, people can see each other and talk to each other. As you can see on the first-person view video, users are represented with a sphere that is the head and with a headset and 2 hands. And so we see that the first view person is sharing object with the other one is putting object together, and then the structure is moving. So then we also implemented a separated workspace. So this is the individual workspaces that I was talking about earlier. So in these workspaces, the 2 participants are now in two different rooms, and they each have their own individual educative material. So as you can see on the first-person view video, the person is manipulated its own object, and it's still possible to hear the other person, so to talk with the other person. Just it's not possible to see anymore what the other is doing, nor its avatar. And so finally, we wondered if an in-between would be possible. So to have the advantages of the collaborative learning and at the same time the benefits of the individual workspaces. So we implemented a replicated workspace. So here you can see that the 2 users still have their own educative material, but now they are in the same room. So in the first-person video, you can see that the person is manipulating its own object once again, but now you can see in the background what the other person is doing. And you can still, once again, hear the other person, talk with the other person. So that's it for our 3 workspaces. And now you may be wondering what these people are doing with all these colored cubes. So our task is inspired by a task design for problem solving from education literature. And so it's a real-time problem solving task that promotes manipulation and reflection. And we put that into virtual reality. So in this task, you have to assemble cubes in order to create a signal that will allow the structure of cubes to move. Especially this black cube is a proximity sensor, and it will create a signal when the user puts something in front of the captor. So for instance, a hand, a cube, or the table. The blue one is a switch on off, and the yellow one provide a feedback to the user on the value of the signal. And then with that, we added a mystery cube. So we have 3 different mystery cubes because it's a within subject study. And we asked participants to discover and describe the effect on the signal of the mystery cube. So here you can see in the separated workspace in the first person view that the person is putting cubes together, putting on the structure. And then when they put their hands in front of the structure, it allows the structure to move. And when the person is putting the yellow cube, you will see that it gives a feedback on the value of the signal. So the signal was 100%, so the bar was completely green. So that's it for the task. And then for our hypothesis, we have 2 different categories of hypotheses. So first, on learning and problem solving. So these hypotheses are supported by literature on education. So first, we think that there is going to be less exploration of the problem solving space in our shared condition, and so more exploration in the replicated and separated workspaces, because people have each their own material, so they will be more likely to explore more this problem-solving space. We also think that there is going to be less interaction with the material overall with the shared workspace, and so more with the others, because people will be more likely to interact when they are not sharing the material, when they have their own material. And for task comprehension, we think that it's going to be better in the replicated condition, because while it's possible to explore and to interact with your own material, it will also be possible to build on each other's knowledge quite easily, because you can see the other person, you can see what the other person is doing. And then we have hypotheses on social presence. So these are supported by literature on immersive technologies. And for that, we think that social presence and awareness is going to be less good in the separated workspace, because people are likely to have to recreate a common ground in order to collaborate together. And we also think that there is going to be less communication overall in this workspace, and that there is going to be more communication when people can see each other avatars, and what they are doing. So first, I'm going to focus on learning and problem solving. And switching to results. So for exploration of the problem-solving space, we measured that by counting the number of unique configurations of cube made by participants. So we counted unique configuration of 4 cubes because participants needed at least 4 cubes in order to learn something on the mystery cube. And we can see that there is a statistical difference between the shared workspace and the 2 other workspaces, with less configuration of 4 cubes in the shared one. So we validated this hypothesis. And we also checked for configuration of 5 cubes, but we could only see a tendency and no statistical differences. For the interaction with the material, we measured that by counting the number of time participants grabbed the educative material, so the cubes. And here we can see also a statistical difference between the shared workspace and the separated and replicated workspace, with less interaction, so less grabbing of the material in the shared workspace. So we validated this hypothesis. And we also checked how this interaction were balanced between the 2 members of the dyads. So in this graph, 50-50, so the equal participation would mean that the 2 persons manipulated equally the material. But as you can see, there is a statistical difference between the shared workspace and the 2 other workspaces, meaning that in the shared workspace, it was more likely that participants, that one of the participants will manipulate overall more than the other one, while the other one was not manipulated, or at least less manipulating than the other one. And for task comprehension, We measured that by asking participants 2 questions. So first, what is the effect of the mystery cube? And then an application question where they have to use their prior understanding on a new hypothetical cube configuration. But we found no statistical differences, so we could not validate this hypothesis. And now for the results on social presence. First, for social presence and awareness, we measured that with self-reported questions. So here you can see that there is statistical differences between the 3 environments with more social presence and awareness in the shared and replicated workspace. For questions such as, I found it easy to carry out the task in interaction with a person, or questions such as, I was aware of what the other was doing. But we can also note that social presence was particularly better in the shared workspace. And then for the amount of communication, we measured that first by counting the number of words pronounced by participants. And we were quite surprised because we thought that the communication, that there was going to be less communication in the separated workspace. But what we found was actually a statistical difference between the shared and the replicated workspace, with more communication in the shared one than in the replicated one. And we also measured that by asking self-reported questions to participants. So how often did they communicate verbally? And we found a statistical difference between the shared workspace and the 2 other one, but no statistical difference between replicated and separated workspace. So we could not validate this hypothesis. So now for the highlights of this paper. Having your own workspace indeed promotes exploration and especially a more balanced interaction between the 2 members of the DIADs. But we could not find any difference on the task comprehension. And also, replicated workspace is not really an in-between in the end, especially regarding social presence and communication. But this could be explained by the fact that our replicated workspace was quite restrictive. For instance, participants could not share objects with the other one, so it might be one of the reasons. And for future work, it will be very interesting to study qualitatively the communication even more, especially the creative communication. So what I mean by that is when participants, especially when they know each other, they are really likely to use very creative communication, so to rely on their common ground to describe objects and situations. And it can be very difficult to analyze for the experimenter when you don't share this common ground with the participants. So I think it will be very interesting to study a bit more that, and especially in context with a longer task in order to have a longer reflection during this task. Thank you for listening, and don't hesitate to ask questions on this work.
Yes. Thank you for the presentation. And is there any questions from audience?
Thanks for your presentation. I think it was really interesting and something similar that we've been working on before. Looking at the 3 different spaces, I think the tasks are a bit different. Like in the shared space, they are doing the task together. In the others, they are doing it separately. So I think that might affect the result. Have you considered having this kind of separated space on a task that they are actually working on together? So they would maybe have to pass the cubes to each other through the wall somehow, and kind of work on the same task similar to the shared space, but being separated in different spaces, but being able to communicate.
Can you reformulate the question? I'm sorry.
Sure. I mean, about the separated workspace. So have you considered that with a common task that they are working on together? So they would have to pass the cubes, for example, through a hole in the wall to the other person. So they would still work together on a task instead of doing the tasks on their own, and considering how that would affect the results.
We have not done that for now, but yeah, it will be very interesting to implement other techniques of collaboration to improve this awareness. But in the separated workspace, especially like this condition, we also use that because after talking with teachers, professors, they said that usually when the students were doing manipulating work, they asked students to imagine that they were in a different room from the other ones and like to explain what they were doing. And so in this condition, it was kind of this idea also. And what happened was actually that they were trying to recreate common ground and to do sometime like the same configurations to be sure that we're doing the same things. But so yeah, implement new techniques for that will be a very nice future work.
Okay, is there any other questions?
Thank you for your presentation. My question mostly relates to the social presence questions used. Did you use a standardized questionnaire like the network minds, or because I didn't see that, so I don't know.
Yeah, no, it was not a standardized questionnaire. We use our own questionnaire by picking question on a standardized questionnaire that was in order to have questions that were really made for this task.
Thank you.
Okay. Yeah, let's thank the speaker again, and then move to the.
Good afternoon, everyone. Today, I will share our work on coordination in VR collaboration, PACT, Perceptual Asymmetry Coordination Theory. We examine what happens when collaborators view the same space at different scales and how they recover after breakdown. Let me start with a scenario. Imagine you're working with a teammate in VR. You're zoomed out, looking at an entire machine, and you point and say, look at that part of the wheel. But your teammate is zoomed in 5 times, inspecting a single bolt. They respond, where? I only see the board. This is the coordination paradox. You're both in the same virtual space, but your visual experience have completely split apart. At different scales, normal coordination cues break down. Gestures lose meaning because there's no common reference point. Gaze becomes unclear, and words like this or that vary entirely. The result, you're virtually together, but perceptually disconnected. Shared space does not guarantee shared perception. Most current research focuses on preventing this problem, designing systems that keep everyone aligned. But here's the thing. In VR, difference views aren't a bug. They are necessary. Users need to zoom in for details and zoom out for the big picture. Breakdowns aren't rare. They are inevitable. This raises a crucial question. What happens after alignment fails? How do teams actually recover? Or why do some teams fail to recover at all? Our focus shifts from prevention to recovery, systems that help teams adapt after breakdown occur. This raises us 3 research questions. First, how do coordination methods change under scale differences? We want to understand what happens to the signals and strategies teams use when their views diverge. Second, what patterns enable teams to recover effectively? What separates successful adaptation from failure? And third, what patterns explain persistent failure? When teams can re-establish shared attention, what's going wrong? These questions guided our study and led to the PACT framework. To analyze coordination systematically, we developed a 2x2 framework based on 2 factors: who initiate the cue and how noticeable it is. This gives us 4 types. User explicit includes deliberate actions like pointing and saying, look at this. User implicit includes subtler behaviors like head orientation or body posture. On the system side, system event-based mechanisms are discrete interventions, like a visual highlight that appears when someone repeatedly fails to coordinate. And system continuous mechanisms are persistent guides like directional arrows or loom labels that are always present. This became our framework for analyzing coordination in the study. Our study involved 108 participants in 36 teams of 3. Every team experienced both conditions. In the low scale condition, everyone's locked at the same scale, a baseline where everyone saw identically. In the high scale condition, members could freely adjust from 0.2 times to 5 times, with an average difference of 3.8 times. Within teams, substantial divergence. Each team completed 3 collaborated tasks per condition, and we analyzed 425 coordination episodes, moments where teams attempted to establish or repair shared attention. We designed 3 tasks to test coordination under scale differences. Joint classification required categorizing objects where shapes were only visible zoomed out, but texture only visible zoom in. This forced the teams to coordinate across different views. Spatial assembly involved building structures where some parts were small and hard to identify without zooming in, while others required overview for correct placement. Information integration asked teams to answer questions by interpreting clues scattered across multiple rooms, small labels, diagrams, and markers. Although these tasks varied, they created the same fundamental challenge, different views that disrupted coordination and required recovery. Our first major finding, users-driven coordination break down sharply under scale differences, while system-driven mechanisms remain stable. User explicit cues, like gesture and verbal reference, dropped down 69%, success 58% under high variance. User implicit cues dropped even more, from 61% to 46%. But system event-based cues remained stable at around 70 to 73% across both conditions. System continuous cues declined somewhat, but less severely than user-driven cues. Why? Because user actions depend on shared views, pointings, gauge direction, spatial reference. When scales diverge, these signals lose their grounding. But system-generated cues are anchored to objects in the environment, not user perspective. This tells us something important. The coordination tools we take for granted become fragile in scale different VR. Our second finding reveals a critical failure pattern we call the persistence loop. This is what happens when teams get stuck. They try something, say, pointing, and saying, look here, it fails. And then instead of trying something different, they repeat the exact same thing, often with more intensity, louder voice, bigger gesture, but no actual strategic change. The pattern was consistent. Try, fail, repeat the same approach, fail again, frustration builds, eventually give up. And this was common. The persistence loop appeared in 65.2% of failed episodes, compared to only 18.7% of successful ones. It was the strongest predictor of failure. The problem wasn't choosing the wrong method. The problem was not recognizing when it wasn't working and lacking the flexibility to shift strategies. But a successful team did something different. They showed adaptive recovery through structured transitions. We identified 3 patterns. Orientation, a system highlight draws attention, then a user clarifies with speech or gesture. The system prompts, the user focuses. Synchronizations, a soft user cue escalates to explicit communication, then gets system reinforcement. It's a layered, multi-step process. And adaptation, an ambient cue triggers a corrective system event, redirecting attention when subtle signals aren't working. These adaptive transitions appeared in 73% of episodes from high-performing teams, but only 54% from low-performing teams. The key, successful teams didn't just use multiple methods. They transitioned between them fluidly, adjusting based on feedback or the lack of it. This replaced the persistent loop with recovery pathways. Let me make the contrast clear. High-performing teams used multi-channel strategy 61% of the time. Low-performing teams only 34%. High-performing teams averaged 1.9 strategy transitions per episode. Low-performing teams just 0.8. And high-performing teams shifted the strategies within 10 seconds of failure 67% of the time, compared to 29% for low-performing teams. The bottom line, success was about strategic flexibility, detecting misalignment, and responding adaptively. Failure was defined by rigidity. Teams stuck in persistence loop had low transition rates, relied on single strategies, and missed the recovery opportunities even when alternatives were available. But here's a critical detail. Recovery doesn't just depend on using multiple methods. It depends on timing. In successful episodes, cues were tightly coordinated, usually within 5 seconds. A user points and within 2 seconds, a system highlight reinforces it. The timing creates a coherent layered signal. But in failed episodes, there were long gaps with no adaptation. A user make a bid, 8 seconds pass, they repeat the same bid, another long gap, missed recovery opportunities. Multi-channel strategies are not automatically robust. They depend on timing, spatial alignment, and perceptual accessibility. PACT treats queue integration as a dynamic, time-sensitive process. So what does all this tell us? It led us develop PACT, perceptual asymmetry coordination theory. PACT models coordination not as binary state, aligned or not, but as trajectory that unfolds over time. After breakdown, teams take one of two paths. On the left, adaptive recovery. Teams recognize misalignment, shift strategies, use multi-channel cues, execute structured transitions, and successfully restore shared attention. On the right, the breakdown path. Teams show rigidity, rely on single strategies, enter the persistence loop, and coordination fails. The key insight, recovery opportunities exist at multiple points along the trajectory, but only adaptive teams seize them. PACT reframes coordination as a process of breakdown, recognition, and repair, not a fixed state to maintain. So PACT extends 3 foundational theories in collaboration research. It extends grounding theory from establishing common ground to recovering after failures. Traditional grounding assumes relatively stable views, but PACT addresses what happens when those frames diverge. It reframes media richness theory from matching channel quality to task needs to strategic redundancy across multiple channels. In scale different contexts, no single channel is sufficient. Strength comes from layering diverse, overlapping cues. And it revisits distributed cognition from assuming shared understanding to modeling how teams adapt when that understanding collapses. PACT highlights that coordination is also a temporal process of repair. Together, this position PACT as a bridge between classical theories and the unstable conditions of immersive collaboration. So what does this mean for design? PACT suggests 3 principles for building recovery-ready VR system. First, detect and disrupt. Don't wait for frustration. Monitor coordination failures, like repeated ignore speeds, and intervene early with general nudges. Show a subtle tooltip, like try describing it aloud. or fade and ignore the gesture to make breakdown visible. Second, the scaffold transitions support the choreography of coordination, not just isolated cues. Link actions in time. If a user point then speaks, reinforce both together. Design for sequences, not single events. Third, enable redundancy without overload. Layer cues, gesture trails, more gaze raise, highlights, but differentiate them visually and manage it density adaptively. Redundancy isn't noise, it's resilience. This represents a shift from enforcing alignment to supporting adaptive recovery. Let me close with a core message. Misalignment in immersive collaboration is inevitable. The goal is to recover through it. Coordination adapts within breakdown when teams flexibly reestablish shared perception. The persistence loop shows what failure looks like, rigidity and missed opportunities. Adaptive recovery shows that success requires redundancy, timing, and responsive transitions. The future of collaborated VR isn't about preventing misalignment. It's about systems that detect breakdowns early, guide adaptive transitions, and scaffold resilient coordination. Because breakdown isn't failure, it's where coordination becomes adaptive and robust. Thank you for your attention. You can also reach me at email or Discord. We plan to release the dataset and the program published. Thank you.
Yeah. Thank you for the presentation. And any other questions from audience? Okay, I have just one small question. Like, since you, I observed the group of the participants is quite the group. Yeah, the participant group is 108 participants. So have you considered this factor as the different participants may have different perceptual abilities? So do you analyze the factor diversity, like participant diversity as a factor in your framework?
If I got your point correctly, participant diversity.
Yeah, yes.
Sorry. If you're asking about the diversity of our participants in our current study, the most participants were university students with a limited prior experience.
Okay.
In scale-based VR collaboration, we intentionally used a relatively homogeneous group to control for external variability and focus on the perceptual asymmetry shift.
Okay.
So, yeah, however, we recognize that more diverse backgrounds, such as professional designers or more remote industry teams, could reveal different coordination dynamics. Expanding participant diversity is definitely part of our future work. So, to test our broadly packed, generalize across expertise levels and collaboration culture.
Okay. Yeah, thank you for the answer. And if we have no other questions, let's thank the speaker again.